Boom, quick, do this problem. All right, so I got the problem loaded in. I've got our 25 amps of current that are separated by 10 centimeters, and I've got the permeability of free space in here as well. I've been saying it incorrectly, and it's in the notes incorrectly as well, so I do need to change that. This is not permittivity, this is permeability. But either way, to find that value, this is just going to be mu naught I over 2 pi r. So we are just going to plug that in. It is going to be mu naught times I, and then that numerator is divided by 2 times pi times our r. And so we find that the magnetic field is a small value, 5 times 10 to the negative 5. So even with this large amount of current, the magnetic field that's around this value is fairly small. The last thing that we have to figure out, though, is the direction of this magnetic field. If our wire is behind the wall, using our right-hand rule, our thumb points up vertically, then our fingers are going to curl around it. If our wire is behind where we're measuring, then you should find that your finger should point to the right. Okay, picking up where we left off with electromagnetic induction. And so this guy over here is Michael Faraday, and he's the one who discovered Faraday's Law of Induction around 1830. And this picture of him right here is from an episode of Cosmos, the Neil deGrasse Tyson one. It was a pretty interesting episode, I thought, to hear the story of Michael Faraday. He had a lot of struggles to get to where he needed to be as a research scientist. So the whole idea of Michael Faraday's law works sort of like this. In the previous unit, so back in circuits, if we wanted current to flow in a wire, we needed a battery. The only way that we were going to get current to flow through a wire was with a battery. And so that means that moving this magnet has to act as our battery in this setup. Instead of having some battery to move current through, we can just move a magnet around. And that moving magnet is going to create something called an induced current. And so the idea of Faraday's law is that moving magnets can produce current as well. But what he found is that the magnet doesn't even have to go into the loop. It can just be near the loop. And that will still give us some kind of induced EMF. And so when I say EMF, we saw it on WebAssign last week as well. EMF stands for electromotive force. It's really just a voltage. Back in the past, before we knew this whole idea of voltages and the electric field pushing electrons through the wire, back when we thought that it was positive charges that were moving through, we knew that there would have to be some force to push them along the wire, and we called it an EMF. Now it's pretty much just interchangeable with voltage. And so if we wanted to figure out what induced current was going through this loop, we need to talk about something called flux. And so magnetic flux is how much of the magnetic field is passing through an area. And so you can see in the formula right here, this symbol, capital Phi with a subscript B, is our magnetic flux, and it's measured in units of Webers. And then you've got your magnetic field strength, capital B, and then you've got area as well. But note that this is not just multiplied. This is the same symbol that we had back in our work unit. This is the dot product. So when you're finding magnetic flux, it is B dot A to get to your result. So what you want to do is you want to think of magnetic flux. What you want to think of phi B right here in our formula. That is just the number of field lines that pass through some surface. And so you've got your magnetic field, which has field lines or arrows that leave from the North Pole and enter into the South Pole. And if we put just a loop of wire near that magnet, we would just want to count up how many of those field lines are passing through that loop of wire. And this is why we need the dot product right there. Because if we look at these pictures down here, if the field lines are going right into that surface, if they're parallel to this dotted line, which is our normal, then all of the lines are going to pass through. If it's at sort of an angle, on the edges here, there's going to be field lines that don't pass through that little blue rectangle. And if we're completely perpendicular, then none of the field lines are going to pass through the little blue rectangle there. They're all going to either move above or below that blue rectangle. So the picture on the left has maximum flux when the cosine is 0. And the picture on the right is going to have minimum flux when cosine is 90. Okay, so what we want to do is we want to find the magnetic flux through this circular hoop at 30-degree intervals. So we're going to take that hoop and we're going to rotate it 30 degrees each time. And we're going to do that until we've gone a full 180 degrees. So this loop is basically facing the other way. So let's use the radius of the hoop as 0.5 meters, and let's say that the magnetic field, which is going to the right of the screen, is 12.73 Tesla. Using that magnetic flux formula, we just have to calculate what phi b is going to be. And so, if we show just the first one, where we haven't rotated at all, phi b is going to be b dot a, which is ba cos theta, and when we plug in our stuff, we get 10 Webers. And so 10 Webers is going to be the most flux that we can have going through this setup. If we rotate it by 30 degrees, though, now the only thing that's going to change is that we have to use the cosine of 30 right in there. And so once this rotates a little bit, we can see that the magnetic flux goes down. And we rotate it further, and it rotates more, and the flux goes down more, until we get to 90 degrees when we have no flux at all because none of the field lines are going to pass through that hoop. So now, if we think about this, once we go past 90, this arrow, which represents the normal to this loop, is going to be going in the opposite direction. It's going to be down in like the third quadrant. And so our angle is going to be greater than 90, and we could expect that this number should be negative. In fact, it is. It's going to be negative 5 Webers. And then if we keep going to the next number, at 150, we're at negative 8.7 Webers, until we're at a full 180 when we're at negative 10 Webers. The same value that we started with, but negative sign because it's in the opposite direction. So this is an important distinction to make. If the field lines go anti-parallel to the normal, meaning they're parallel but in opposite directions, you're going to get negative flux. So that's field lines that are coming into a surface. Whereas field lines that are leaving a surface, so now you've got these two things that are parallel, and that's going to give you a positive value for Webers. Okay, so we've got our definition for flux, which is how much magnetic field is going through a surface, but we saw in the experiment that it's not just magnetic field passing into that loop. The magnet has to be moving as well. And so that's the important thing about Faraday's law, is it's not just the flux that is giving us some kind of EMF, it's a change in flux that is giving us an EMF. And another thing that is not immediately obvious from the experiment that we did is the number of loops matters as well. If I used more loops, we would have a larger value for EMF. And so here we go. This is Faraday's law of induction. We can say that our EMF, or our voltage, which is another way to think of it, is equal to negative N, which is the number of turns in our wire, times the change in flux over time. And so if that flux doesn't change, like if we just left the magnet in the loop, we don't get any voltage at all. But if we were to change that flux very quickly, like move the magnet into and out of the loop as quickly as we could, then we would get a large voltage. And similarly, we can get a much larger voltage by having more loops of wire as well. If I had covered that whole piece of copper with loops, we could have had a larger result as well. So this right here is called Faraday's law of induction. And this is how we figure out how much voltage, induced voltage, exists in a circuit because of some moving magnetic field. And so this process right here is very important to things like generators. Generators work off of this idea right here. You've got some kind of moving magnet, which is then going to produce current that you can use to do some kind of work. Okay, so let's give this one a try. We've got this 10-turn loop of wire, even though it doesn't look like 10 turns. Trust me, that's 10 turns. And it's got a radius of 2 centimeters. And we want to rotate it from being parallel to this 5 Tesla magnetic field to being perpendicular to this 5 Tesla magnetic field. And let's assume that that rotation takes 1 second. Let's try to calculate what the induced EMF would be in this coil. Give this a try, and then we'll see if our numbers match.
Zach, stop! Zach, stop! You're gonna get in trouble. Zach!
Okay, so let's give this problem a try. I've set up this table so that we've got spots for our initial information, spots for our final information, Then up here in the corner, we can find our changes. And then lastly, we can get to our final answer. And that's kind of the way that these problems always go. You find your initial flux, you find your final flux, just using B dot A. Then we're going to take their difference. That's going to give us our change. You divide by time to get your change in flux over change in time. You multiply by your turns, and then you've got your EMF. But don't forget that the EMF should be negative. It's negative N delta phi over delta T. So let's start by plugging in what we know. The magnetic field doesn't change. It's 5 before, and it's 5 after. And we know the area isn't going to change either. That is just a circular loop of wire. And so it is just going to be pi times r squared. In this case, our radius was 0.2. So again, on this side, pi times r squared. Great. Initially, we were parallel to the field. So that's an angle of 0. And we're going to move to perpendicular to the field. So that's going to be 90. Nice. So now we just have to calculate these fluxes using B dot A. Whenever you do a dot product, that's the cosine of the angle between your two vectors, in which, in this case, we're talking about the magnetic field vector and the normal. So we're just going to do B times A times the cosine of this angle. And we have to remember that Excel doesn't work with degrees very well, so I'm going to change that degree into radians just so that it can calculate it. And so this is our initial flux, about 0.63. And then we can calculate the final one as well using the same formula. And I'm going to type it out just to show you what you should get. But we already know going into this that we're using an angle of 90. And so we should have some intuition about what that flux should be. And thankfully the formula matches at least what my intuition was, which is that we shouldn't have any flux. We should end up with no flux at all when we're perpendicular to, when our area is perpendicular to our magnetic field. So now we're going to take our difference. A change in something is always final minus initial. And we know that our time that it took to do this was 1 second. We know that we had 10 loops that went into this. So it's just going to be 10 turns times the change in flux over time. And so we end up with, don't forget to make this negative like I did. And so we're going to end up with an EMF of about 6.3 volts. Great. So if we do this whole problem, we end up finding that the induced EMF in this coil should be about 6.3 volts once we rotate it like this. And so for that 1 second of rotation, we're going to have about 6.3 volts. And then once it stops right here, all that induced current disappears. Before that moment when we're rotating, we should have a value of 6.3 volts, which we can, we could calculate if we had a resistor in there, how much current that resistor is receiving, and we can do all the things just like we did with circuits. But the question then becomes, which direction is current actually traveling in? Is that current going clockwise, or is that current going counterclockwise? And to figure that out, we have to use Lenz's law. Okay, so going back to the notes right here, we've got Faraday's law, which is that a change in flux over time gives us some kind of voltage. And so as this loop moves around, or as this loop gets bigger or smaller, or maybe as the magnetic field increases or decreases, if there's some change to the magnetic flux, we're going to get a voltage. But the thing about this whole setup is that nature abhors any kind of change like that. It does not want things to be different than how it was before. So if you think back to other similar examples like that, we've got all these conservation laws. We've got like conservation of charge, we've got conservation of energy, we've got conservation of momentum, we've got conservation of angular momentum. And if you think about like the demonstration that I had with the bicycle wheel would fall over unless it was rotating, and then it would stay up vertically. And it's kind of the same idea here. When you change that flux through a surface, nature is going to do something in order to try to maintain that same amount of flux. And so when we talk about Lenz's law is right here, and it says simply that an induced EMF creates a current to oppose the change in flux. And so it's a little bit counterintuitive, but let's look at this picture right here. So on the left-hand side, we've got some loop that has 4 magnetic field lines going through it. And let's say that this loop is able to be increased in size or decreased in size. And so at some point in time, it has 4 field lines passing through it. And then we're going to increase the area. When we do that, we can now have 6 field lines passing through it. That's a change in flux. And nature is going to do something to try to decrease the number of field lines passing through there, to try to maintain that 4. Nature is going to essentially induce a current that generates 2 magnetic field lines going down to cancel everything out and leave us at a net of 4. And how do we figure out what that change is going to be? That's from our right-hand rule. So your thumb is going to point in the direction of the induced magnetic field. The induced magnetic field is just the magnetic field that nature creates to cancel out those extra lines. We started with 4. Now we've got 6. So nature is going to induce a magnetic field that points downwards with a strength of 2 of those field lines. And then our fingers are going to curl in the direction that they would want to, and that is going to be our induced current. So our thumb is the induced magnetic field that nature is creating to oppose that change, and our fingers curl in the direction of that current. So if you had some loop and increased it in size when it's sitting in a magnetic field that's pointed upwards, you're going to get some kind of clockwise current if you were to look at the loop from the top down. It's a lot, and it feels like you're dealing with double negatives, so let's try another one just to make sure we're a little bit comfortable with this, at least as much as we can be with these weird online learning circumstances. So same loop, 4 field lines that are pointing up, and now we're going to decrease the size of that loop. So in going from 4 field lines to only 2, nature wants to create some amount of magnetic field to make up that difference so that there isn't any change at all. So nature wants to create a magnetic field that is essentially 2 field lines of strength pointing up. So if our thumb is that induced magnetic field, our fingers are going to curl the way they naturally would, and that's our induced current, which in this case, from looking at the top of the loop down, is going to be counterclockwise. And this is Lenz's law. Lenz's law says that an induced EMF is going to create a current to oppose the change in flux. Okay, so let's think about this setup a little bit more closely. We've got this movable wire that can go left or right, and by doing that, we're going to change the flux, and when we change the flux, we get some voltage that's induced. And so let's try to calculate what that voltage would actually be. So whenever you find these voltages, the first step is always going to be to find the change in flux. So let's find the initial and final flux. So here is the initial flux, and it's just going to be B dot A, and so BA cos theta. And we know also that the field points in and the normal for the area points in, and so this is just going to be the cosine of 0, and I can ignore it. And that's going to mean that our flux is just our magnetic field times our area, and our area is this length times this width. So I can call that BLW. And then the final flux is going to be very similar. The only thing that's going to change is that we're going to have some different W. So this will be BLW final, and let's just call that W initial. So now we have these 2 fluxes we can plug into Faraday's law. So Faraday's law says that your EMF is negative N, and we only have 1 loop in here, so I'm going to leave that N out. So it'll just be negative times 1 of our change in flux over our change in time. So we just plug in. Final minus initial is going to be BLW final minus BLW initial all over T. And we've got a BL in both of these, so we can just pull that common factor out and make this negative BL times WF minus WI all over T. And if we look at this picture a little bit more closely, if this is our width, and we're just talking about moving this thing left or right for different times, this is really just a velocity. It's a change in distance over time. So we can make this new formula, which is negative BLV, And this thing right here is a special case of Faraday's law, which we call the Hall voltage. So this device right here, where you move this wire in or out, depending on how quickly you move that wire, you can get a different voltage, and we call that the Hall voltage. So we can see that this is the setup that we were just talking about with this movable wire that can go towards or away from the resistor. And this is the formula that we just derived for the Hall voltage. So this induced EMF in the wire, which is this curly E, this epsilon over here, is equal to magnetic field strength B times the length of that movable wire L times the velocity of that movable wire V. So BLV would give you this induced EMF in the wire. And that's it for magnetic fields. I think that it would be a good idea to end this video by asking you guys to try this problem in red right here. Moving the wire towards or away from the resistor is going to create some induced voltage. And let's try to find out what current we get out of that if we know that this resistor here is 100 ohms and the magnetic field it's sitting in is 0.1 Tesla. Let's say that this movable wire has a length of 2 centimeters and it's traveling at 10 meters per second. Let's try to find the current through that resistor and then see if you can use Lenz's law to figure out the direction that the current's flowing in. You do have a 50-50 chance. So, as always, email me if you have any questions, and we'll start tomorrow by going over this problem.